Dr. Mourad is one of the Department of Mathematics, Cairo University, who graduated from the same department, and our cooperation continued for a very long time. He's a very famous person in the field of orthogonal polynomials and fractional calculus. We welcome him today to give us the first part of a two-part seminar. Please, Dr. Mourad.
Okay, shukran. Okay, well, thank you very much for the invitation. Can you hear me well?
Yes, sure.
Okay, so let me just start with something, sort of standard. So this is the oh, I think this is from you. Okay. So if you start with the this partial differential equation, so this is an initial value problem. At time 0, you specify the function, and otherwise it satisfies this partial differential equation. And you want to solve this. Okay, we teach this. I mean, any course in PDEs, I mean, you do heat equations, wave equations, this and that, and so on. So the solution can be written this way. Okay, so there are some scratches on the.
I don't know from where this is appearing.
It's not from me because I cannot touch it here. It's anyway. So the solution, you can write it like this. Okay, that's not hard to do. But the point of this representation is that if I denote this side by WF at t, because now this is a function of t here, and it's a function of x as well. So if I denote this by WF and t, then this W has this property that if I go to time t plus s, if I start from time 0 and go to time t plus s, I get the same as if I start from time 0, go to time s, and then start from time s and go to time t. So it just depends on the duration, not where your initial step is. So this property is the semigroup property, which I'll write it formally. And in addition to this property, you also should have that as time goes to 0, this object has to go back to f. So what you have here is you have a semigroup of operators. So that's this t of t. So t at t1 acting on t at t2, so these are now operators, is t at t1 plus t2. And if I let t tends to 0 plus, I get the identity operator. So that is this condition. Okay, so this is the abstract Cauchy problem. I want to look at semigroups that have this property. But this problem started from this PDE, so there should be some analog of this. And the analog indeed exists. And so that is the analog of, that's the second derivative operator. And that comes from something called the infinitesimal generator. So suppose now I take t at t plus h minus t at t and divide by h. H here is a scalar, so this is an operator well defined. Now, because of the semigroup property, I can take t of t out, and that's what is left, because t at 0 is 1, is the identity. So this object is called the infinitesimal generator, if it exists. Well, this here is very tricky because This will not be defined everywhere on the space that you have. For example, if you expect something like this, this is not defined on all continuous functions or all differentiable functions. When derivative, you require certain smoothness for it to be defined. So this thing usually is defined on a basis rather than globally like this. But the point is, if I can calculate this object, this is the infinitesimal generator, then this thing at any t is just the semigroup acting on the infinitesimal generator. And if you go back to this semigroup and you calculate its infinitesimal generator, it is indeed this operator. So the Cauchy problem, the abstract Cauchy problem, is buried into this. And what the abstract Cauchy problem is, it's the infinitesimal generator acting on W is w dt and the initial condition. That's the exact analog of the heat equation that we started with. Okay, so this is the general definition of a semigroup and what an infinitesimal generator is and where it came from. The next thing is the Riemann-Leoville fractional operators. So this is the fractional integral. It's defined this way. And this forms a semigroup. If you take I alpha, I alpha acting on I beta, you get I alpha plus beta. And I guess this should be alpha, not A. Okay, so there is this, and it has the semigroup property and so on. And when alpha tends to 0, this tends to the identity. So this forms a semigroup. And the adjoints also form a semigroup. So the adjoint operators are these. Okay, now one important property for these operators is that, they're called fractional integrals. So somehow they should be inverses to derivatives. So if I denote the derivative operator, the d dx denoted by d, if I take d and act on a fractional operator of integral of order alpha, I get a fractional integral operator of order alpha minus 1. That's because if I integrate alpha times and differentiate once, I should get integration alpha minus 1 times. The same thing for the other operator, for the Weil fractional. It's also the same. Well, okay, so now we have a semigroup, and the next question is, what's the infinitesimal generator? Well, do this as an exercise, especially you, Zainab, because you wrote a book about the fractional calculus. So that is, the infinitesimal generator can be calculated in this case. And what is more important is that there are Q analogs of all these, and for some reason, nobody looked at the infinitesimal generators or the abstract Cauchy problem that comes from the Q fractional integrals. I have no idea why. I think I know, because most of the people who worked on this early on did the formal properties, like try to solve equations with it, see connection with Laplace transform, do something like that. But they didn't go deeper into the analytic questions. And this certainly is something important, to look at the abstract Cauchy problem associated with the fractional, with the Q fractional integral operators. And what is the corresponding abstract Cauchy problem? I don't think anybody looked at this. Okay, another thing is, if I take the Laplace transform and I act on the fractional integral, I get s to the minus alpha times the Laplace transform of f. This is a very trivial formula to prove, and the reason for it is that if you look at the this integral operator here, it's a convolution So of course, when you take a Laplace transform of a convolution, you get product of Laplace transforms. So it's not surprising that you have something like this. But the point here is that this thing is now called a multiplier. Okay, so what is a multiplier? You have a some transform. So a multiplier will be if you take the transform applied to some operation acting on a function, and then you get something times the operator acting on the function, the transform acting on the function. So this is an example of a multiplier. I'll show you other examples very soon. And the mathematical questions associated with this are what is the range of these fractional integral operators? And in general, if I have a transform, how can I describe the range of it? The next question is to characterize all multipliers for such transform. So for Laplace or Millen transform, etc. Now, many people worked on this in 1950s till 1990s. These are just some names. And there's a lot of stuff on describing the ranges, describing the multipliers, etc. Now, knowing the range is important because if you want to invert, usually you see this kind of formula, which says if I integrate n plus a times, and then I integrate 1 minus a, so this with this becomes n plus 1, integral n plus 1, and then if I differentiate n plus 1, I should get the function back. So this tells me how to get f from this. However, if I try to use this, I have all kinds of issues because this here has to be in the domain of the next one. And the action of this on this, so now that's the range, has to be in the domain of the next one. So all these problems somehow, when you read things on fractional calculus, are overlooked. So you do need to be careful in describing exactly what spaces these are. Okay, and okay, so here is another example. This is a very old one, and this is where the multiplier is started. It's with Fourier series. If I take a function in L2, capital L2, and this is its Fourier series, then if I have an infinite sequence, Cn, I want to know under what conditions, if I take this function here, I take its Fourier coefficients, multiply them by this sequence, and I want this one here to represent a capital L2 function. In other words, I have the Fourier coefficients, I modify them, I multiply them by some sequence, and then I want the new sequence to be Fourier coefficients of another function in L2. So can I describe what conditions I have on Cn? This is sort of the baby version of the multiplier problem. And of course, the idea is this. I know what the Fourier coefficients are. And then all I want to do is multiply this by Cn. So for example, if Cn is bounded, I know that I can do this. The reason is, Cn is bounded, these coefficients will be in little l2. I have a bounded sequence times a sequence in little l2. The product is in little l2. Hence, there is a function, by the Riesz-Fischer theorem, there is a function whose Fourier coefficients are these. There is an L2 function, a unique L2 function, whose Fourier series is like that. So this baby problem here is very easy, but it's the one that started the whole thing, the question of multipliers, historically. So the very first part was very modest, but then things evolved. Okay, one other important ingredient is what's called Korovka and Theorem. So the x to the j, I call it ej of x. And if I have a sequence of positive linear operators acting on continuous functions on a compact interval, then if I know that this sequence converges uniformly for j equals 0, 1, and 2. Okay, so if the action here on the constant function 1, on the function x, and the function x squared, if it converges to the functions, then it converges on all continuous functions uniformly. So, I mean, this is an amazing theorem because all you have to do is to test it on 3 functions, and it will automatically approximate all continuous functions. So one example, for example, of this is the Bernstein polynomials. So Bernstein gave a constructive proof of the Weierstrass approximation theorem. He defined Bn f at x to be this sum. Okay, so the f here is f of k over n. F is defined continuous in 0, 1, so that's where these values are. And if I compute this object, I get a polynomial, obviously, of degree n. And if I let n tend to infinity, here I recover the continuous function f. And this is uniform on 0, 1. His original proof, of course, was different, but if you do Korovka and Theorem, all you need to do is take f here to be 1, x and x squared, calculate this, make sure that this thing works for 1x and x squared, and then it works for everybody. I mean, it's an amazing theorem. And what is interesting is its proof is actually not much harder than the original proof that Bernstein gave. I mean, Bernstein really had, in his proof, if you read it carefully, he did use the action on the 3 functions, and then he, from there somehow, he found the general convergence. So Korovka and Theorem is very important and very useful. And there is another transform called the Gauss-Weierstrass transform, which is this. We have seen this before. This is exactly the one I started with, this one. And instead of 2t, I have a 1 over lambda. So instead of this 2t, I have a lambda on top. And instead of this 4, 2 pi, and the 2t, gives me a lambda on the top. So in approximation theory, this operator is called the Gauss-Weierstrass transform, and it forms it converges to the function but now the intervals are unbounded. Okay, so in approximation theory, the reason you're interested in things like the Bernstein polynomials or like this transform is that it improves the smoothness of the function. For example, if f is a continuous function, the Bernstein polynomial is a polynomial. I mean, it's the simplest thing of all. And here, this is a C infinity function. So if I start with a function, I need some growth conditions for the integral to exist. But if I have the function continuous with certain growth conditions, this thing is C infinity. So these operators improve the smoothness of the function, and that's why people use them to approximate functions. Okay, and in this, of course, there is a semigroup behind the Weierstrass, the Gauss-Weierstrass transform. As I told you, if you replace lambda by 1 over 2t, you get the semigroup. But for the Bernstein polynomials, there is no such thing. It doesn't form semigroup under any condition. Okay, so far what we did, I just defined what these fractional integral operators are, and I told you what multipliers are and what transforms are, and this Korovka and Theorem, which reduces the question of convergence to just testing it on 3 functions. Okay, so the next thing is some application to orthogonal polynomials, which I did a long time ago. You slightly modify the fractional integrals. The fractional integral had, the Riemann Leoville had this. It didn't have this u to the lambda, but that's not a big deal. You just incorporate it with the f if you wish. And there is the adjoint. That's this operator. And the Jacobi polynomials are 2f1 functions. The Jacobi polynomials are orthogonal -1, 1. So this quantity here, the variable in the hypergeometric function is between 0 and 1. Okay, so instead of saying that the Jacobi polynomials are orthogonal -1, 1, I'm going to call this y and say y is in 0, 1. Okay, so now this is the one with the y, or I just call it x now. And what I did, this was a long time ago. This was known. I mean, it's not like I discovered it, but it was known that if I take these fractional integral operators and act on a Jacobi polynomial, I get another Jacobi polynomial. If I do the adjoints, I get another Jacobi polynomial, but instead of x, I have 1 minus x. Okay, so this looks like some calculus exercise, and it really is a calculus exercise. However, it's very useful because using this, I showed that these Jacobi polynomials are eigenfunctions of an integral operator. And the integral operator is a symmetric kernel. So the kernel is complicated, but you can get it from these formulas. It's sort of a long story. I don't want to tell you what the long story is, but you can do it. You can use just these and some ideas to find out that these Jacobi polynomials satisfy this equation, integral equation, and that this is a symmetric kernel. The kernel is like that. Okay, now once you do this, what do you get out of it? You get, you know that the kernel can be expanded into this bilinear formula. So these are the eigenvalues, and these are the eigenfunctions, and this is just the Hilbert-Schmidt theory, that the kernel of a symmetric integral operator can be expanded in terms of the eigenfunctions. Again, the conditions here, you either use L2 or you use L1. I mean, you use pointwise, but it depends on Mercer's theorem and so on. There are some cases where you can prove that converges pointwise, and there are some cases where this is an L2 theory. But you can get this. Now, more importantly, you can iterate these kernels and find, like these lambda n's, you can find something similar with lambda n squared, but now these will be different, and lambda n cubed, and so on. So you can get not only this family, but families like this with square here and cube here and so on. So you can get all kinds of things out of this fractional integral operators. You can get these bilinear expansions. Okay, and what was used is the fact that you change, you map a Jacobi polynomial to a Jacobi polynomial, and that's it. That's all that was used. So let's go back and take another look at what this formula does. Okay, so what is this formula here? Well, you integrate some sort of complicated kernel against this, and you reproduce this function. But let's go back here. Okay, so if I apply this operator to Fn, I get another Jacobi polynomial. Okay, what is this called? Well, this is sort of a relationship connecting a polynomial of degree n as an integral of the same family, another polynomial from the same family of the same degree. So this n is the same as this n. In other words, here what you're doing is you're integrating over the variable somehow and producing this function. Okay, there's another thing in orthogonal polynomials, which is this. If I take Jacobi polynomials, I have all degrees. So I can expand Jacobi polynomial with set of parameters alpha beta in terms of Jacobi polynomials with parameters gamma delta. This expansion exists. It's linear algebra. It's trivial. These are bases, and I'm just writing the connection coefficients for the bases. But what's not trivial is finding these coefficients. These coefficients are usually very hard to find, and in many cases you can just prove their positivity. If you can show something about their signs, that's one of the things that people do in special functions. They look at the sign behavior of these things, whether it's always positive or changes sign or what. If it's always positive, that means there is some geometry behind it. For example, if you do the spherical harmonics, if you do this case for the spherical harmonics, if these things are positive, that means that you have a Euclidean space, say n-dimensional, and you have another k-dimensional Euclidean space. And what you want to do is you want to have an isometric embedding of one of them into the other. So of course, if k is less than n, you can embed the k-dimensional in the n-dimensional. And that fact has something to do with the spherical functions, and for that, it's necessary and sufficient that these things are non-negative. So it tells you something about the geometry involved where these are spherical functions. Okay, so again, this is a standard problem in orthogonal polynomials, how to expand one set of polynomials into another. And what this is a continuous analog of that, because you see here, this n, the x is the same, but the degrees change. But in here, the degrees are the same, but the variables change. So this formula, or the transmutation relation, is a continuous analog of this discrete relation. So this is one of the things that people do in special functions, to do these connection relations and determine the signs of these coefficients. And their positivity usually has some geometric property. Okay, now there are other operators other than derivatives. For example, the finite difference and the skew difference. And the fractional powers of these have been studied. There is this lecture note by Nabi and Mansour, which is, how old is it? It's like 5 years or maybe more. I don't remember when it appeared. It appeared recently anyway.
2012.
2012, okay, so 8 years. Okay, so Al-Salam and Verma started looking at the skew fractional integral operators. Originally Al-Salam did, and then Al-Salam and Verma did some Leibniz rules and so on. And for the finite differences, there are also results. There are fractional powers, etc. But again, these multiplier issues and so on, and the ranges and so on is not done. It's not known. Okay, so the last thing I want to mention today is the Askew-Wilson operator. So this is something more complicated than the operators that you saw here, but yet it's really the most important. Okay, so this appeared first in their memoir, 1985, and I have to go slow here because okay, so you change variables. Your x, you write it as z plus 1 over z. Okay. This is like writing cosine theta as e to the I theta plus e to the minus I theta over 2. Then any function of x, I can write it as a function of z after I change variables like this. So my f of x defines f check of z. And now the operator is defined on f check. So I dilate z by q to the 1/2 and q to the minus 1/2, take the difference, and divide by what this does if the function were x. So this is like delta f over delta x. Okay, so again, I replace x by z plus 1 over z, and I do dilation on z. Okay, now this has its origin back in trigonometric series, because the Chebyshev polynomial of the first kind is cosine n theta. So cosine n theta is a polynomial in cosine theta of degree n, and that's what this Tn is. Also, sine n plus 1 theta over sine theta is a polynomial of degree n in cosine theta, and that's the Chebyshev polynomial of the second kind. So this is Chebyshev polynomial of the first kind, and this is Chebyshev polynomial of the second kind. They both have degree n in the variable. So this is exactly, this cosine n theta is exactly like if I have, if I take this, replace z by e to the I theta, this becomes e to the I n theta, e to the minus I n theta over 2, that becomes this side. So that is like the x to the n, you see. Okay. Now, let me do a calculation here. What I want to do is I want to convince you that I can actually calculate this operator, the action of this operator on Tn. Now, after I do that, if I can calculate it on these polynomials, then by linearity, it's a linear operator, I can calculate it in any polynomial, because just expand it in Tn and use it. Okay, so let's do the example. Cosine n theta is Tn of cosine theta. So my cosine theta is z plus 1 over z over 2. So my z is e to the I theta. Okay, so this is now my f. It is z to the n plus z to the minus n over 2. So that is my f check. And when I write it in terms of z, so my f check of z is z to the n plus z to the minus n over 2. Now I calculate this magic difference. I dilate by q to the half and q to the minus a half and subtract. I put this 2 here, cancel some stuff. Okay, so if I do that, I go here, this 2 cancels the 2. So I here replace z by q to the half z, and here I replace z by q to the minus a half z. So here is the q to the n over 2. That's the first term, q to the, and this one, that's this term. And then when I replace, instead of q to the 1/2, q to the minus a half, this becomes minus and this becomes a plus.
Can I ask a question, please?
Yeah.
Actually, I don't understand the Askew-Wilson operator. In the first part, I understand that z is in the unit circle.
No.
Z equal e to the I theta is in the unit circle. So z.
Oh, no, it's not. Who said theta is real? No.
No, I am speaking about the next paper, please. Here. Z equal e to the power I theta, so it is in the unit circle.
No,
so
it's not, because theta is not real.
Theta is not real?
No.
So when you write 1 over z, you didn't mean the conjugate. You mean 1 over z.
Yes.
So it's not necessary that q to the power half z, that its absolute value equal to 1. This is not, because I always don't understand this part, because I thought
No, theta, no. This parameterization, this I can always do, because I can, if I write x, see, if I write x as this, and multiply both sides by z, I get a quadratic equation in z. So if I want to write z in terms of x, I get something plus or minus a square root. So I have to choose the appropriate sign. I have to define the principal part of the square root, or I have to define which branch I take. Once I define that, it's defined uniquely. Because you see, otherwise, if theta is always real, then this would always be in minus 1, 1. No, it's not.
Okay.
No, minus 1, 1, no.
Yeah, but the Tn and Un functions are defined for theta real.
No, they're not.
They're not?
No, because these are polynomials in the variable cosine theta. Cosine theta is a complex variable.
So x is a complex variable. X equal cosine theta is a complex variable, not real variable.
That's right.
Yeah. That's why I don't understand.
Is it a polynomial? No. It's not a real variable, no.
Okay.
Okay. All right. So after I do this calculation, this miraculously factors into this. And of course, this quantity is sine n theta with a 2i, and this factor is there. Okay, so now I go back and calculate this delta f over this quantity, over delta x. So here is the delta f is on the top, and the delta x, the difference between cosine n theta and cosine theta is that n is 1. So if I want to calculate what the denominator is, I just take this and put n equal 1. So it becomes like that. And then this is a Chebyshev polynomial of the second kind, and this is just a number. So if I look at this formula, it says if I act on Tn, I get Un minus 1 times this number. And if you look at this number carefully, as q tends to 1, this tends to n. So this operator indeed tends to the differential operator as q tends to 1. This is not obvious at all from the definition, but after you do this, at least on polynomials, it's clear, and at least it makes some sense. Okay, so now the point is that this operator is like differentiation. It's linear. It maps a polynomial degree n to a polynomial degree n minus 1. And I know how to work with it with the Tn. Okay, so now once you have this, you start asking questions. Okay, what about doing calculus again, but now for this operator? For example, do we have a Taylor series? What is the analog of x to the n? What's the analog of e to the x? What's the analog of all these questions? All of this has been developed over the years. The Q-Taylor series I developed with Dennis Stanton. The powers, the analog of powers, there are these Esky-Wilson bases, which acts like powers. Okay, what's so special about powers? If I differentiate x to the n, I get n times x to the n minus 1. So what I want is I want some function where if I act with the Eskew-Wilson operator, I get something like this times the function at n minus 11. And there are three bases that would do this. There are three analogs of x to the n. One of them was found by Eskew-Wilson. The other two, Dennis Stanton and I found over the years. So there are these. There is the Taylor series. There is the exponential. I worked with Ruming Zhang a long time ago. It was part of his thesis. And there's a whole theory for the Eskew-Wilson operator, which is very, very similar to the derivative. There are all kinds of complications because, for example, the null space of the Eskew-Wilson operator is not the constants. And if you look at the definition, the null space will be when this is 0. So an f check at q to the half z is the same as f check at q to the minus a half z. So that means that f check does not change if I replace z by qz. So that is not a trivial. This is the null space, and that is not the constants. That's much bigger. So you have to be careful when to use this because if the Eskew-Wilson operator acting on a function is 0, it's not a constant. There are integral representations. There are all kinds of things that can be developed for the Eskew-Wilson operator. So what I will do the next time is I will go back to all these questions which is try to define fractional integrals. So I want to have a semigroup, and from the semigroup I want to be able to have this property. So the property is yes. You see the derivative acting on an integral of order of alpha minus alpha is I alpha minus 1. So not only that I want to develop this I alpha, the analog of I alpha, to be a semigroup, but I also want the Eskew-Wilson operator, when it acts on it, it reduces the same by 1. So I have to this is a fundamental issue here. Also, we'll study the corresponding abstract Cauchy problem. We'll describe the eigenvalues and eigenfunctions of the operators and so on. So we will study this in some detail. There are still some questions left, but I think we understand how it will work. So the next time, what I want to do is to define what Poisson kernels are, and from there get the key to the fractional integral operators. Okay, I think I better stop.